In this lecture, we will use frequency response methods to design a lag compensator. Specifically, we will first review what we know about lag compensators. We will then examine the frequency response of a lag compensator and use that to understand what the effect of adding lag compensation to a closed-loop system is. And finally, we will present a procedure for designing lag compensators with the Bode diagram and go through a detailed example. So recall what we know about lag compensators. Here is the form of a lag compensator. It consists of a single zero and a single pole and possibly a gain. So it has the same structure as a lead compensator, which we just covered, except with a lag compensator, the zero is larger than the pole. Whereas with a lead compensator, it's reversed. The pole is larger. The effect of having a smaller pole, having a pole that's closer to the imaginary axis than the zero, can be sort of interpreted as the pole dominating. The idea with a lag compensator is that the fact that the zero is larger than the pole, if we look at the DC gain of this portion without the k at all, we can determine the DC gain by taking the limit as s goes to 0. The DC gain of this is equal to z divided by p. And since z is larger, that means that the DC gain of the pole 0 combination is greater than 1. The effect of increasing the DC gain of our open loop system tends to have the effect of helping the steady state error. So that is sort of the basic reason to add a lag compensator, to improve the steady state error or reduce the steady state error. Recall that earlier in the semester, we used the root locus to design lag compensators. And specifically, the approach we took was we used the ratio z over p to achieve the desired steady state error. So whatever the specification was, we used the final value theorem to pick the ratio of z to p to achieve a certain steady state error. Once we achieved that ratio, we then chose to place the pole and the zero near the origin so that they essentially canceled one another and so that they didn't have much of an effect on the transient response. So, we got this ratio, let's say 10, and then we just placed the pole and the zero near the origin, something like 0.1 and 0.01. So we get the ratio that we desire, so we get the effect on the steady state response that we desire, but the effect of the pole and the zero on the transient response cancels because they are so close to one another. You can sort of imagine if you were trying to satisfy the angle condition to any point on the root locus, you could see that the angle from the zero and the angle from the pole are almost identical. At this point, we're actually going to use frequency response to not only achieve the desired steady state response, but also to affect the transient response in a way that we want. So whereas with the root locus, we just tried to not affect the transient at all, with frequency response, we will be able to control to some degree what the effect of the lag compensator is on the transient response. And so at this point, we'll go ahead and take a look at the frequency response of the lag compensator. So we recall that this is the form. We'll leave out the gain for now. We have a single zero and a single pole. This is not in Bode form, so I'm going to go ahead and factor out a z in the numerator and factor out a p in the denominator. This gives us a gain and a simple zero and a simple pole. For future reference, we'll define this ratio between z and p to be a variable beta. And since z is larger than p, beta is greater than 1. And so looking at this, we can use the approach that we've used previously where we take each of the components, the gain, the zero, and the pole, plot their Bode plots individually, and then add them up. In this case, I'm going to try and do it all in one step. If you have some trouble following what's happening, that's okay. You could always do the three components individually and sum them up so that you can see where this Bode plot comes from. But looking at this, these guys have a DC gain of 1 or 0 dBs. So at low frequencies, this determines the magnitude of the Bode plot. And specifically, if we change it to decibels, it's equal to 20 log of Z over P, or 20 log of beta. Okay. Then we'll have break frequencies for the 0 and break frequencies for the pole, where this is sort of T for the 0 and this is T for the pole, and the break frequency is located at 1 over T. So we'll have a break frequency at Z for the 0 and a break frequency at P for the pole. And since the pole is smaller, that's the first break frequency that we'll encounter. So we'll encounter the P first and then the Z later. So initially we're flat. When the pole enters in, the pole adds a slope of minus 20 dBs per decade. So the slope will start to go down. When the 0 comes in, the 0 adds a positive slope of 20 dBs per decade. So when the 0 comes in, we'll have a slope of 0 due to the gain, a slope of plus 20 due to the 0, and a slope of minus 20 due to the pole. And so the plus 20 and the minus 20 add to 0, and so the total slope is also 0. And so this is the basic shape of the magnitude plot of the lag compensator. Looking at the phase, at low frequencies, a 0 has 0 phase, a pole has 0 phase, and a gain that's positive has 0 phase. So at low frequencies, we'll have a phase of 0 degrees. We'll then hit the pole first, a decade below that break frequency. So 0.1 P. And that causes the phase to drop down to 90 degrees in the limit. That's what a pole does. A pole starts at 0 and goes down to minus 90 degrees. And so we'll start to go down to minus 90 degrees. We may get there if the pole and the 0 are far enough apart. We may get all the way down to 90 degrees. If we don't, a decade before the 0 will level off because the pole makes the slope go down and the 0 makes the slope go up, and they sort of cancel out. Eventually, the pole runs out, and so then the only slope left is the 0. Eventually the pole flattens out, and so the 0 will come back up, and it stops a decade after the 0. And then at the higher frequencies, the 0 goes to plus 90, the pole goes to minus 90, the gain stays at 0 the whole time, and so plus 90 degrees added to negative 90 degrees adds up to 0 degrees, and this is where the phase goes, and we get this sort of shape. Okay. Again, if you had trouble following that, you can do it step by step. You'll notice the shape is very similar to what we had for a lead compensator, except for a lead compensator, the magnitude went up because the 0 came first and the pole came later. And similarly, instead of the phase going down below 0 degrees, the phase went up above 0 degrees before coming back down to 0 degrees. If we try to draw this not as a straight line, we would have more of an S sort of shape for the magnitude, and for the phase we would have a smoother sort of bump. And the maximum amount of phase lag occurs at omega m, is what we'll call it. We'll call it omega m, where the maximum dip in the phase is. And that is located at the geometric mean between the pole and the 0, just as it was with the lead compensator. looking at the frequency response, we can get some sense of what its effect is on the closed loop system. So if we imagine that this lag compensator is in series with our plant, then the Bode plots will just add when we look at the open loop frequency response. The Bode plot of the compensator will add to the Bode plot of the plant. And so the effect is that it will tend to increase the magnitude at lower frequencies. And again, the reason that that's desired is because it helps to reduce the steady state error. The benefit of the lag compensator is that we're able to get this higher gain at low frequencies without increasing the gain at higher frequencies. And there's a few advantages to that we'll show. Looking at this phase lag, in general, reducing phase or eating away phase is a bad thing. It tends to make the system less stable, eats away at our phase margin. And so the solution that we're going to use in designing our lag compensator is we're going to try and keep this dip in phase away from the gain crossover frequency, because the gain crossover frequency is where we determine the phase margin. Okay, so I'm going to try and summarize what I just said here a little bit on the next slide. Summarizing what we saw on the previous slide, the lag compensator tends to increase the DC gain of the open loop system. And so the benefit of that is that it reduces steady state error. The benefit of using a lag compensator instead of just trying to reduce all of the steady state error with a simple gain is that we're able to get the higher, larger magnitude at low frequencies while not increasing the magnitude at higher frequencies. And so the effect of that, by keeping the gain lower or the magnitude lower at higher frequencies, is it tends to attenuate noise better. Since it moves the gain crossover frequency to a lower frequency, that also helps, it tends to help increase the phase margin, which is a good thing. And while the lower gain crossover frequency implies slower response, it's beneficial in that it generally requires less control effort. So we may be slower, but it doesn't require as much control effort to get the resulting performance. So that might be hard to see some of these benefits, but I'll try to point them out as we go through a more detailed example. The phase lag added by the compensator, we will attempt to keep it away from the gain crossover frequency so that it doesn't have an adverse effect on the phase margin. At this point, I'd quickly like to point out the relationship between a lag compensator and a PI compensator because their effect is so similar. And so we'll do that by looking at the frequency response of the PI compensator. Recall the structure of the PI compensator where the control is calculated as being proportional to the error plus a term that's proportional to the integral of the error. So this is the proportional control constant, and this is the constant that is proportional to the integral of the error. If I get a common denominator by multiplying the Kp by S and dividing the Kp by S, I get this form where I can see that the PI compensator adds a 0 and it also adds a pole at the origin. This doesn't have the Bode form, so I can factor out a Ki to get this form. So I have a simple gain, I have a 0, and then I have an integrator. So looking at the magnitude plot, we'll see that the 0 has a break frequency at 1 over t, where this is t. So it has a break frequency at Ki over Kp. I'll go ahead and make the assumption that this break frequency occurs above 1 radian per second, but that's not really necessary. So if it occurs above 1 radian per second, we'll see that the magnitude at 1 radian per second will just be the magnitude of the gain. So the 0 initially has a magnitude of 0 dBs. The integrator at 1 radian per second has a magnitude of 0 dBs. And so the total magnitude will just be due to the gain. So it'll equal 20 log Ki. And so at those lower frequencies, the slope will be entirely due to the integrator. And then when the zero enters in, the slope will flatten out because the integrator has a slope of minus 20, the zero has a slope of plus 20 dBs per decade. You add them together, that adds up to 0. Looking at the phase, we'll have a break 1 decade before the 0, hypothetically. And then it stops 1 decade after. At low frequencies, the 0 has a phase of 0 degrees. The gain always has a phase of 0 degrees, and the integrator always has a phase of minus 90 degrees. So it'll be 0 plus minus 90 for a total of minus 90 degrees. It'll then start to change 1 decade before the 0 break frequency. It'll start to go up, and it'll finish going up 1 decade after the 0 break frequency at 0 degrees. And so if you look at this, the shape is quite similar to a lag compensator. It tends to increase the DC gain, whereas with the PI compensator, it goes up and the magnitude goes to infinity at low frequencies, whereas with a lag compensator, it'll level off. With the phase, similarly, with the PI compensator, the phase goes to minus 90 degrees at low frequencies, but with a lag compensator, the phase would come back up to 0 degrees. And so they have very similar behavior in the sense that they tend to increase the magnitude at low frequencies without necessarily increasing the magnitude at high frequencies. The minor differences are that the PI compensator can sometimes add more phase lag, especially at low frequencies. The other difference is that to implement a PI compensator, you have to use an active circuit. You have to use an op-amp in order to do the integration, whereas with a lag compensator, that can be implemented using a passive circuit constructed just of resistors and capacitors. At this point, we'll now quickly go through the procedure for designing a lag compensator using frequency response methods. The procedure might not be totally clear at this point, but we'll go into more detail as we do an example. So the first step is to set K to achieve the desired steady state error. So we're going to go ahead and define K to be equal to this quantity. And so in effect, K is going to be what increases the DC gain. That's how much we want to increase the DC gain by, where some of that increase will come from a simple gain, Kc, and some of it will come from the ratio of the 0 and the pole. Once we've set the desired magnitude at low frequencies, we'll then go ahead and reduce the magnitude at higher frequencies with this ratio of Z to P. So the bigger that ratio, the bigger the reduction in magnitude at higher frequencies. And specifically, we're going to set the reduction to achieve a crossover frequency that gives us the desired phase margin. We'll then go ahead and center the pole in the 0. Step 2 will give us the ratio between Z and P. Step 3 will allow us to specifically place Z and P in a particular location. And the way that we'll do that is we'll center the geometric mean of the pole in the 0 to center the maximum amount of phase lag 1 decade below the new gain crossover frequency. And the reason we put that bump in phase lag below the new gain crossover frequency is so that it doesn't adversely affect the phase margin too much. Step 4, we then calculate Kc. So we knew what the total K we wanted. We know what the ratio to Z to P is that we want. And so we can simply divide to get Kc. And then finally, we'll check the results. So the thing that we sort of need to keep in mind is we're going to have these rough approximate relationship between frequency response parameters and time response. but these relationships are only approximate, especially when we don't have canonical second-order systems. And so in order to verify that we're actually getting the time response that we want, we have to check the time response and then tweak the compensator to get the frequency response we want. So again, some of these steps might not be completely clear, but we're going to go through a more detailed example to help illustrate. So here's our example. We have a plant, we have a lag compensator, and we want to design the lag compensator to achieve a steady state error less than 0.01 for a unit ramp reference, and to achieve overshoot, a maximum percent overshoot of less than 10%. So the first step in our procedure is to set K to achieve the desired steady state error. Recall that we're defining K to equal these two parameters multiplied together. So K is basically the desired increase in DC gain, where some of that comes from a gain K sub C and some of it comes from the ratio of the zero and the pole. I'm going to go ahead and give the remaining portion of the transfer function a name G sub C. And so the way that we're going to set K is to use the final value theorem. Before we can do that, we need an expression for E of S. We can do that by first finding the transfer function from the reference to the error. Looking at the previous slide, we have a negative feedback loop, so we use the standard form forward over 1 plus loop, where the forward path from the reference to the error is just 1. So we have a 1 in the numerator, and then the denominator we have 1 plus loop, where the loop consists of the compensator and the plant. And so the compensator has this form, K times GC of S times the plant. I'll go ahead and plug in for what the plant is. I'll keep the K and the GC for the compensator. The plant has a numerator 72,000, has the denominator with a pole at 0, pole at minus 36, and a pole at minus 100. I can then clean this up by multiplying through by this denominator. So I get a numerator of S times the quantity S plus 36 times the quantity S plus 100 divided by S times the quantity S plus 36 times the quantity S plus 100 plus the K times the GC of S, which is left over. I can then go ahead and recall the form of the final value theorem. E steady state is equal to the limit as S goes to 0 of S times E of S. Where E of S is equal to this transfer function multiplied by R of S. So I just multiply through by the reference to isolate E of S. So I have this whole expression. I'll repeat it quickly. Multiply it by R of S. In this case, we're trying to achieve a certain level of steady state error for a ramp input. So R of S is equal then to 1 over S squared, because that is the Laplace transform of a ramp. This S squared will cancel with that S and that S. What remains then presumably has poles that are stable, or at least we'll make sure to design our compensator so that's true. So it's defined at S equals 0, the final value theorem holds. We can just substitute in S equals 0. This whole term will go away because we'll have 0 times this quantity. In the numerator, I'll be left with 36 times 100. Then I'll have K. This portion of the compensator transfer function has a DC gain of 1. I've also left out the 72,000. So there's also a 72,000 in there. Of K times 1 times 72,000. And we need that to be less than 0.01, let's say less than or equal to. If I solve for K, multiply the K to the other side, divide through by the 0.01. I need that K be greater than or equal to 3,600 divided by 0.01 times 72,000, which is approximately 5. So in order to meet our steady state error requirement, we need K to be larger than 5. We're going to go ahead and choose K to be as small as we can get away with. Because that'll meet the steady state error requirement. And if we make K any larger, then it's going to push the gain crossover frequency to a higher level than necessary. The next step of our procedure is to set the ratio of the zero and the pole, which we are calling beta, to achieve the desired phase margin. So in essence, the beta is the amount of reduction in magnitude that we're going to get at higher frequencies compared to the lower frequencies. And we're going to set that reduction in order to set the location of the gain crossover frequency to achieve the desired phase margin. Okay, so again, that might not be very clear. It'll become more clear on the next slide when we actually look at the Bode diagram. We're also going to add an extra bit of phase margin or desired phase margin in order to account for the phase lag that's going to be added by the compensator. So in this case, we desire that the overshoot be less than 10%. And so that means that we need the damping ratio to be greater than this quantity. So if we punch that into our calculators, we get that the damping ratio needs to be greater than approximately 0.6. If we recall, we know that damping ratio is related to phase margin. And so this relationship, it's only approximate, and it's worse if we're not dealing with a canonical second order system. But we're going to go ahead and use it as a starting point anyways. So we need our zeta to be approximately greater than 0.6. So if we multiply through by 100, that means that our phase margin needs to be greater than approximately 60 degrees. And this relationship isn't exact, but it's at least going to give us a starting point. Okay. So this is what we need in order to achieve that amount of overshoot. We're going to go ahead and add this extra 10 degrees to account for the phase lag that's going to be added by the compensator. So we're going to shoot to add about 70 degrees of phase margin. So we're going to shoot for a phase margin of about 70 degrees. Okay, so here we have our Bode plot. The blue line is the plant. The red line is with the gain K. So this is our K. And as we can see, adding the gain shifted everything up. It improved our DC gain, which is going to help our steady state error. So that value for K is what's going to get us to meet our steady state error requirement. We then want to reduce this overall gain. So we don't want to get all of it with the pure gain. We want to get some of it with our pole zero relationship, pole zero ratio. And so we're going to get a reduction in magnitude at higher frequencies due to this Z over P. The bigger the ratio, the bigger the reduction in gain we're going to get. And so specifically, we're going to choose the reduction in order to achieve the desired phase margin. So on the previous slide, we saw that we're going to shoot for a phase margin of about 70 degrees. And so it turns out if we plot this in MATLAB and zoom in, this gets us about 70 degrees right here. So this occurs at about 9.5 radians per second. And so as it stands, our gain crossover frequency is way out here. And so we need to move our gain crossover frequency to 9.5 radians per second. In order to do that, we need to reduce the magnitude that much. Again, if we take a look at this plot in MATLAB and zoom in, we can see that we need to reduce the magnitude by about 20 dBs, or to be more exact, 20.1 dBs. And that's specifically going to come from the ratio of Z to P. So in order to achieve a phase of 70 degrees, we need the crossover frequency to be approximately 9.5 radians per second. So we need a reduction in magnitude of 20.1 dBs. And so specifically, we can figure out what that is for beta by thinking of the fact that converting something into decibels, we take the logarithm and multiply it by 20. And so in order to solve for beta, I divide through by 20, and I raise both sides to the power 10. Get beta is approximately 20.1 divided by 20. So that's about 10.1. This determines our ratio of Z over P. So, ultimately, we want the K to be about 5. This is going to allow us to reduce Kc to a value that's actually less than 1 in order to achieve the amount of reduction we want to achieve the phase margin we want. Okay. So at this point, we've established the ratio between Z and P, but we haven't placed Z and P exactly. And so step 3 will allow us to do that. And we're going to set this new maximum frequency where the maximum phase lag is 1 decade below the new gain crossover frequency. And so since the new omega C is approximately 9.5 radians per second, we'll set omega M to be about 1/10 of that. And so we have that we want the ratio of 0 to pole to be about 10.1. We have that we want the geometric mean of the 0 and pole to be approximately 0.95. We have 2 equations and 2 unknowns, so we can solve for both Z and P. If we do a little algebra, we get that the pole is located at approximately 0.30, and the 0 is located at approximately 3.02. So we've defined Z over P. And then we can find Kc just by dividing. So we know that K is equal to Kc times beta. So Kc is simply K divided by beta. So we want to reduce the DC gain or we want to increase the DC gain by a factor of 5, but we're able to get more than that from the zero pole ratio. And so that means that we can actually decrease the gain that we have to add to less than 1. Okay, so this gives us our first sort of pass at our lag compensator. We've defined Z, we've defined P, and we've defined the gain K sub C. And so the last thing we need to do is we need to double check, because these relationships that we are using are only approximate. So first off, we can check the Bode plot. So this P is our plant, or the blue line is our plant. The red line is our plant with our compensator. And we can see a couple things. We can see that we've increased the DC gain to reduce the steady state error. That we can be certain of, because the final value theorem doesn't rely on any sort of approximations. That holds no matter if it's a second order system, a third order system, it has a 0 or whatever. We also see that we've moved the gain crossover frequency to a lower frequency. So we've achieved this improved DC gain, but we've slowed the system down so that presumably this new compensator will cause the system to need a smaller amount of control effort. And we've also placed the bump in our phase lag away from the crossover frequency. So this crossover frequency is at approximately 9.5 radians per second. We move the dip in phase lag about a decade below that, and so that it doesn't hurt the phase margin too much. It has a little bit of an effect there, comparing it to the blue line, but not a ton. If we look at what the actual phase margin is, we look at the gain crossover frequency, and we see where the phase is relative to minus 180 degrees. We see that the phase margin is approximately 54 degrees. So this is a little bit smaller than we were shooting for. We were actually shooting for 60 degrees. So we might not have gotten the overshoot that we desire, but we need to check anyways because those relationships were approximate. So if I go ahead and look at the closed loop step response, this is what I get. And I can see that the overshoot is much larger than the 10% that I desired. And this is because of two things. One, we didn't get as much phase margin as we wanted. And plus, we were basing this guess on phase margin on an approximation that isn't exact. Therefore, we need to iterate. We need to retune the parameters of our lag compensator to try and bring the overshoot down. And so we'll continue to use the frequency response. We'll continue to use the Bode diagram to help us in the tuning. And specifically, since the overshoot is too large, we need to increase the phase margin. Okay, to something bigger than 54 degrees. There's a couple things that we can do to help that. So one idea is that a larger beta, a larger ratio between the 0 and pole, will give a larger reduction. So, this drop in magnitude is due to the pole 0 ratio. And so if we use a larger beta, we'll get a bigger drop in magnitude. And what that'll do is that'll cause the phase margin to go to a lower frequency. So a larger beta will move omega C earlier, which increases the phase margin. So if we move the crossover frequency back further, we can see that we've moved from a frequency where the plant itself has more phase margin, has less phase lag. And so that can help us. The other thing that we can do is we can move omega m more than a decade before omega c. So this dip, which occurs at omega m, that's the maximum amount of phase lag, it's still contributing some phase lag in the neighborhood of the crossover frequency. So if we moved omega m even farther back, it would dip and come back to the plant sooner. So these two approaches are things that we can do to help bring the overshoot down, where, again, we'll have to iterate, and we may find that we're not actually able to achieve this overshoot. So we may have to sort of push back on the requirements, or we may have to consider using a different type of compensator. For example, you could use 2 lag compensators. So sort of to conclude, we'll go ahead and think about what the lag compensator does in comparison to the lead compensator we saw previously. So in many instances, a lead and a lag can achieve the same sort of goals. So in this case, we had an example where we were trying to achieve a certain level of steady state error and a certain amount of maximum percent overshoot. And so we could have done that with either a lead compensator or a lag compensator. And so the question is, which is better? And so the answer is, it depends on your specific case, your specific application. And so they can both achieve the same steady state error and overshoot, but what's different is the speed and the control effort. So a lead compensator will tend to be faster. It achieves its decrease in overshoot by adding phase lead to the system, but it also tends to push the gain crossover frequency to a higher frequency, which makes the system faster, which requires more control effort. The lag compensator gets its increase in phase margin by pushing the crossover frequency to a lower frequency where the plant itself has more phase margin. And so the smaller crossover frequency tends to give a slower response, and it tends to require less control effort. And so which compensator to choose really depends on what your needs are. In practice, more control effort requires a larger actuator, it requires more energy, electricity, fuel, etc. It's more expensive. And so in practice, we basically want to achieve our goals in order to be just fast enough. So if we're able to achieve our goals with a lag compensator, we don't need to make the system faster, or we can actually get away by making the system slower, then we should use a lag compensator. If we have to make the system faster, then we can use a lead compensator. A challenge that you can run into is that you may not be able to set the overshoot and the speed both at the level you desire. So in these cases, we would design our compensators to achieve the overshoot we want, and we would just get whatever speed of response we get. If we actually wanted to design for both, we could combine the lead and the lag compensator. So if we wanted to increase the speed to a specified level, and we wanted to reduce the overshoot and the steady state error, then we could combine a lead and a lag compensator together to achieve these different goals. So that brings us to the conclusion of this lecture.